Today's video is going to talk about zeros and multiplicity. So the point at which a function, a zero is the point or points at which a function intersects the x-axis. So we've talked about these before whenever we talked about quadratic functions. And we talked about how whenever you solve a quadratic function, you're actually finding the x-intercepts. And so that's what zeros are. And that goes through all polynomial functions, not just quadratic functions. So a zero is where it intersects the x-axis. So now a polynomial function of degree n can have at most n real zeros. So remember that the degree is the highest exponent in the function. So if the highest exponent is a 3, like x cubed, then it could only have 3 zeros at most. And it wouldn't have to have 3, but it could only have up to 3. All right, an even degree polynomial has an even number of zeros or none at all. So even degree, that's 2, 4, 6, etc. And they have to have either an even number of zeros or no zeros at all. Now an odd degree polynomial has an odd number of zeros. So the first section that we're going to look at when we talk about zeros is how to identify them by graphing. And we're not going to make a table. We're going to use our calculator. So I'm going to show you both Doceri and on a TI-84. Okay, so for a TI-84, the way that we want to graph this function is to click on y equals. So that's right here, y equals. And then we are going to click, or we're going to type in our function. So we use the X key, which is right here above the apps button, and then raise that to the third power plus x squared minus 2x. Okay, so that's what is on our problem over here. Identify by graphing. So we are graphing this, and all you have to do now is press the graph button, and that is this button right here. And you can see here that we have the graph to our function. And we want to identify its zeros, and then we can kind of sketch the graph around it. So on a TI-84, the way that we're going to identify the zeros is just kind of by counting those little dots, and we're going to estimate that it would be at, so here's 1 and then 2. So one of the zeros should be at -2. So whenever we have a 0, we say x equals -2. That's going to be one of the solutions, and that point is going to go right here. Then another 0 seems to be at the origin, which is just 0, 0. So we want to say that another 0 is x equals 0. And that's going to give us a point right here. Then our last 0 looks like it is at +1. And so I'm going to put that dot right here. And then as we just look at the general shape of the graph, we can just sketch it from here. It does not have to be perfect. So, just close enough is fine. But you do want to have those 3 zeros clearly identified and also write them all. And then you can double check that those zeros are actually correct by going back in on your calculator. So all of this writing is going to disappear. So if you need to write it down, go ahead. I can't draw on my screen and use my screen at the same time. But we are going to go to table, which is going to be second and then graph. We're going to click those buttons, and it's going to bring us up to our table. And we decided that our zeros were at -2. So if we scroll to -2 on the x values, we see that that equals 0 as a y value. And that means that we are correct that x equals -2 is in fact a 0 of this polynomial. And if you look at both of our other zeros, we have 0, 0, so that x equals 0 is another one, and then 1, 0. So that is also another x-intercept or 0 or solution or whatever you want to call it. They're all the same. They're also called roots. So let's look at the same problem on Desmos. So if you don't already know, Desmos is the software that I use to make these videos, and then Desmos is an online graphing calculator. But sometimes I say the wrong words. So we just want to graph this function on Desmos, which is an online graphing calculator for people who don't have a TI-84 at home. And you can just type it exactly like it shows up on your paper. And so if you aren't sure what keys to use on your keyboard to type all this in, there is a keyboard down here that lets you do certain things. And so you can also use that. I prefer just to type everything in with my keyboard, but that's okay. Whatever works for you. So when we type this in, we see that we have a 0 here, a 0 here, and a 0 here. And if you take your mouse and you hover, oh, actually I had to click back into this function. So if you hover over each of those spots, it tells you the coordinates. So like up here, it tells me that this is a turning point. Like that's a local maximum is what that's called. So in the future, whenever we need to find those things, this is going to tell us what those are. But here's a 0 and here's the other 0. So once again, you can use Desmos to draw your graph and identify the zeros as well. All right, so if we come back to our graph and our zeros, this is what we figured out regardless of which calculator you've used. Excuse me. So we now need to write this. You should always write this as a solution set. And so what that means is that x can equal all three of these numbers. So we need to group them together in a list. And they get these curly Q brackets around them. So x equals -2, 0, and 1. And that would be your solution set. But you also have to have the graph too. Okay, so you go ahead and try number 2 now. You should find these to be your solutions, but don't forget you have to have your graph and have each point plotted and all that. So make sure you go graph it on a calculator and then come back and, put it on your paper so you get some practice looking at those graphs. All right, so the next section that we want to look at is called linear factors. And I think you guys probably remember factoring. And factoring is something that we worked on for like 2 or 3 weeks straight. And I'm going to talk to you a little bit more about it now. But when we factor things, that's how we found zeros of quadratic functions. So I'm just going to walk you through factoring this equation. It tells us the linear factors of a polynomial reveal its zeros. Linear factors can be found by writing the polynomial in factored form. So if we notice, all 3 of these terms have an x in them. So we can factor out an x like a greatest common factor. And we've done this before. So we have an x, and then that leaves us with x squared minus 2x minus 15. Then, whenever we factor this, remember I told you factoring would come back to haunt you. Here it is. We have 2 x's, and then we want 2 numbers that multiply to get -15 and add to get -2. So I'm going to choose -5 and +3, because -5 times +3 is -15, and -5 plus +3 is -2. So now we split these up, and set each one equal to 0. And that's how we find what our zeros are. So in this one, we have to add 5 to both sides, and we're going to get x equals 5. Sorry, I know that's tiny. I've messed stuff up here. And then on this other one, we're going to have to subtract 3 from both sides, and we're going to get x equals -3. So our zeros are at x equals 0, +5, and -3. So I'm going to write those in order. -3, 0, and 5. Those are the zeros of this function. So we didn't have to graph it at all because we were able to factor it and see them right away. And now that we've kind of refreshed our memory about factoring, we now want to learn a new word called multiplicity. And multiplicity is the number of times that a factor occurs. So I'm going to show you what that looks like in this problem. So we're going to first factor this polynomial, which is like what we just did. We're going to take the x out, and that leaves us with this. And then whenever we factor this middle part, or the part that's still in parentheses, we want things that multiply to get +9 and add to get -6. So it's going to be -3 and -3. So we're going to get a 0 of x equals 0, x minus 3 equals 0, which is going to give us x equals 3. And then again, x minus 3 equals 0, which is just going to give us x equals 3. So these are our 3 zeros, but if you notice, 2 of them are the same. So this asks, what are the zeros and their multiplicity? So we have x equals 0, and it only shows up once. So we're going to say x equals 0, multiplicity, which we're going to abbreviate, of 1. And then we're going to use a semicolon to separate them. And then the next one, we have x. That's a really bad semicolon. So then we have x equals 3 with a multiplicity of 2 because it shows up twice. Also, this could be written as x times x minus 3 squared, because x minus 3 times x minus 3 would be the same as x minus 3 squared. And so in this case, we can also use the exponents, because this is an invisible one, to tell us what the multiplicities are. Okay, so why do we even care what multiplicity is? All right, so when we graph this function, we're going to use a calculator. You can use the calculator of your choice, but I'm just going to go ahead and show you. This is the same function that we just factored and used. We found the multiplicities. So when we graph this, we're going to find that it has a 0 here and a 0 here, which agrees with what we found when we did it algebraically. That means using math. But what I want you to notice is our zeros are x equals 0, multiplicity 1, and x equals 3 with a multiplicity of 2. So if the multiplicity is odd, what's the difference in the odd multiplicity and the even multiplicity? What happens at each of these? Well, when we have an odd multiplicity, the graph intersects, actually I call it crosses. Let's be consistent. The graph crosses the x-axis of that 0. But if the multiplicity is even, then we say the graph bounces at that 0. So if it's odd here, it crosses, and if it's even here, it bounces off. Okay? So let's do an example that doesn't even have a graph with it, okay? We are going to identify the zeros and state their multiplicities. So let's take it one section at a time. This is already in factored form for us, so that is fantastic. So let's take this section first. we're going to have x plus 7 equals 0. So we'll subtract 7 from both sides and we get x equals negative 7. And it has a multiplicity of 2 because the exponent is a 2. So let's go ahead and fill that in over here. We have negative 7 with a multiplicity of 2. And we'll deal with the effects in a minute. Let's do 2x plus 1 next. 2x plus 1 equals 0. So we'll subtract 1 from each side and we get 2x equals negative 1. Then we have to divide both sides by 2 to get x equals negative 1/2. This one has no exponent, so it's understood to be a 1. So it has a multiplicity of 1. Finally, we have x minus 4 to the third power. So we're going to set x minus 4 equal to 0. That will give us x equals positive 4 with a multiplicity of 3. So let's fill the rest of these in because I forgot to do that as we went. So we have negative 1/2 with a multiplicity of 1 and positive 4 with a multiplicity of 3. So now the effect is what we just talked about. Does it cross or does it bounce? So even numbers bounce, multiplicity of 2, bounce. Odd numbers cross. So that's what you want to end up with, is all of this filled in. We want all of those things. So you could imagine if we wanted to draw this graph, so let's pretend that, this is a real graph. We have a 0 at negative 7, so say that's over here. We have we have a 0 at negative 1/2, so that'd be somewhere here, and a 0 at positive 4. So at negative 7 it bounces, and at negative 1/2 it crosses, and then at 4 it also crosses. So it could look like this, but we also have to consider that it could be the other direction. So it could start at the bottom and bounce and go up and cross and cross. And we'll learn more about how to tell which one it is in the future, but right now we just want to focus on the behavior of the zeros. So let's do one more like that. In this one we do actually have to factor again. But this one has a greatest common factor of x squared instead of x, because you just look at the smallest exponent of the variable and you can take that out. So if we take x squared and divide each term by x squared, we're going to be left with x squared minus 2x minus 8. Then we want to factor what's left, and we want things that multiply to get negative 8 and add to get negative 2. So it's going to be negative 4 and positive 2. So this is going to give us x equals 0, multiplicity of 2. X equals 4, multiplicity of 1, because remember we set this equal to 0, so it's going to end up being positive. And then x equals negative 2, multiplicity of 1. So let's move those over here to our chart. We have zeros at 0, 4, and negative 2. Multiplicities of 2, 1, and 1. Even multiplicities bounce. Odd multiplicities cross. So this graph could look like, so it has a 0 at 0, 1 at negative 2, and 1 at positive 4. So we have to start in order. So at negative 2 it crosses. So let's say it starts at the bottom. It crosses at negative 2. At 0 it bounces. So bounce. And then at 4 it crosses. So it could look like that. Or it could be the opposite way. Oops. Like that. Either one would satisfy this, but we will learn later exactly how to tell which one it is. And in the final problem for today's notes, this is making you think a little bit about how to write a polynomial based on the zeros and its multiplicity. So, if we know that a polynomial function has a 0 at negative 6 with a multiplicity of 2 and a 0 at 2 with a multiplicity of 1, and we want to write that polynomial function. So to get a 0 at negative 6, to get x equals negative 6, That means that we had to have set something equal to 0. So we can figure out what that is by adding 6 to both sides. And you'll see that we get x plus 6 equals 0. So that means that this is the linear factor that we must have used to figure out that that's what our 0 was. And it has a multiplicity of 2. So it's going to be squared. Now, our other 0 is at positive 2. So if we got the answer x equals 2, but we needed to figure out what we had set equal to 0, then we need to turn one side to a 0. So in order to do that, we're going to get x minus 2 equals 0. So this was the other linear factor. And it has a multiplicity of 1, but we don't have to write an exponent of a 1. So this is the factored version of our function, but it asks for this in standard form. So we're actually going to have to multiply this all out. So we're going to have x plus 6 times x plus 6 times x minus 2. So we'll start by multiplying the first two together, and we use the FOIL method. So we multiply the first ones, the outsides, the insides, and the last terms. And all of this gets multiplied by x minus 2. But we're going to simplify this first so we don't have as many terms to multiply. So we can combine like terms to get x squared plus 12x plus 36 times x minus 2. So now we're going to distribute each individual term and combine like terms. So I like to go from here because it just, I don't know, I like that better. So we're going to get x cubed. X times 12x is 12x squared. And then x times 36 is 36x. Then negative 2 times x squared is negative 2x squared. And we're combining these still, but I'm just putting them on two different lines because you'll see that our like terms are going to line up this way. All right, the negative 2 times 12x is negative 24x, and then negative 2 times 36 is negative 72. So we're going to add these together. And that's going to give us x cubed plus 10x squared plus 12x minus 72 equals f of x. And that's our function. All right, thanks for listening. Have a great day.